Hi, I'm Neil. Welcome again. This chapter is all about gravitation. Gravity is one of the four fundamental forces in all of nature. So together with the strong nuclear force, the weak nuclear force, and the electrostatic force, gravity rounds out the four basic and fundamental forces that is known to hold the universe together. Gravity is the weakest by far, billions of times weaker than the strong gravitational force, for example, that holds the nucleus together of all atoms that exist. But nevertheless, on very large scales, very massive distances, gravity gives structure to everything, not just the Earth, all planets, but the entire known universe. The structure and the curvature of the universe is predominantly caused by gravitational attraction. Now, unlike forces like the electrostatic force, which is between charged particles, it can be either repulsive or attractive, gravity only works one way. It's an attractive force. You know, many books have been written about gravity, very large books and complicated books, but with that said, the concept of gravity, the nature of gravity, is yet to be fully understood. Even the great Isaac Newton himself, who gave us the universal law of gravitation that governs the universe, he derived the equations, but admitted that he did not understand the true cause, the nature of gravity. And we're still at that point today. But nevertheless, gravity is everywhere. It's an intrinsic property of mass. Wherever there is mass, there is gravity. Now, arguably the two greatest minds to ever live, Isaac Newton and Albert Einstein, they were separated, by more than 200 years, but their genius is unquestioned, and they both had very different takes on the concept of gravity. For example, Isaac Newton in classical physics described gravity as a force of attraction between any two masses. That's what the average person considers to be the definition of gravity today. Albert Einstein, however, used the word attraction nowhere in his definition of what gravitation should be. Einstein defined gravity as the curvature of space due to mass in a four-dimensional space-time continuum. It sounds complicated, and it is. So we're not going to delve into Einstein's theory of gravity. It's well beyond the scope of this particular material. So we'll stick with the classical approach as gravity being an attractive force. So here we've got a picture of what we believe happened about 4 billion years ago. Arguably the greatest, most important and significant day in the history of our home, planet Earth. There have been many milestones in the history of the Earth. Birth of ice ages, end of ice ages, mass extinctions, birth of mountain ranges, the birth of life on the planet, birth of multi-cell life on the planet. There have been many important events that have come and gone in the history of our planet, in the long history of our planet. But if we can narrow this down to just one day, arguably the single most important day in the history of the Earth, it will be the day we got our moon. And very briefly, as the story goes, there was an additional planet in our solar system that formed in similar orbits with the Earth, the young Earth. And these two planets, the gravitational attraction between these two planets outweighed the individual gravitational attraction between each of those planets and our sun, which means that over time a collision was inevitable. As they both orbited the sun, they got pulled closer and closer together, and this is what we believe happened. The fallout from this collision, it made Earth an estimated 20% greater in size, and the leftover material that didn't go into making the Earth larger eventually coalesced out into space at about 239,000 miles away currently to form our moon. So our moon is the leftover, the remnants of this collision between these two heavenly bodies. Now, the reason why this was significant, well, there are many reasons why, but arguably the most significant was that the Earth became more massive, had more material to it now. And like I said, gravity is a function of mass. The more massive Earth had a stronger gravitational influence on its neighbors and was able to trap or to keep this moon that eventually formed from leaving, from drifting into space at too fast a rate. Now, with that said, we are indeed losing the moon. So if you enjoy a good full moon, going down to the beach and looking at that moonlight reflecting off the ocean surface, you should enjoy it while you can, because we are indeed losing the moon. The moon is drifting off into the depths of space at a rate of about 2 inches per year. And if we wait long enough, it is inevitable. We will lose our moon. So enjoy it while you can. What happens when that day comes? Well, we're going to find out, I suppose. But no doubt we will lose our climatic stability. And this is what the larger Earth, after this collision, gave us. A stronger gravitational pull that trapped the moon, and the moon, in tandem with our sun, this triangle, if you will, it created stability of the Earth in space. So it made the seasons more predictable, and it gave us a grip. It gave the Earth a grip on a climate that was more predictable over long periods of time. So it made conditions favorable for all life on Earth. Today, the moon still exerts forces, of course. It creates high tide and low tide, for example. The moon can only face one half of the Earth at any given moment. And that half of the Earth, the ocean waters on that half of the Earth that's facing the moon at any given moment, is closer to the moon. So it sees a stronger gravitational pull. So it pulls the waters onshore, what we call high tide. And of course, that water's got to come from someplace. So where the water is drawn into itself, that generates a low tide. And of course, the Earth takes 12 hours to rotate by 180 degrees. So we see 2 high tides and 2 low tides in every 24 hours. Everywhere on Earth sees those high tides and low tides, to different extents, of course. So this chapter is all about the gravitational influence, not just of the moon on the Earth, but for every object in the entire known universe, because gravity is indeed a universal force of attraction. So if we were to pull up our chapter here on gravity, this is what the reader can look forward to seeing. So we derive the equation. Well, we don't derive, Newton derived the equations, but we show how it applies to the derivation of other phenomena. And so the equation of universal forces is shown in this chapter, and it depends on masses and distance apart and the gravitational constant, which the reader will get into in great detail. But once we have an understanding of the nature of the gravitational force between any two objects, we work out several examples of what this gravitational force would look like. So if I were to turn the lights off, maybe the reader will get a better view. There we go, put it back on. So once we work out several examples of the attractive force between several objects here, we can start off with small objects and move on to much larger ones. We can calculate such things as the gravitational acceleration close to the Earth's surface. That is the g-force, given a value of about 9.8 meters per squared second. What this means is that if you were to drop an object relatively close to the surface of the Earth, its speed increases by 9.8 meters per second for every 1 second it's allowed to fall. So it's indeed accelerating. So we consider some of the consequences of what the g-force is in different scenarios. Of course, this is what gives you your weight. Your mass is effectively constant. It's your weight that varies depending on where you live on the Earth for multiple reasons. But it is the pull of the Earth's gravity on your mass that's equivalent to your weight. So, and this changes depending on your latitude, where you live, whether you live in a mountain or in a cave, how much of what kind of density material is beneath your feet, and this is the function of latitude, because the Earth is not perfectly symmetric, right? It's an oblate spheroid. It bulges at the equator and it's flattened at the poles. So it's quite an interesting thing to be able to, and there is actually a problem that we've worked on in here that it shows what the difference in weight is depending on different places if you were to travel and take a scale with you and use that same scale. It's actually quite interesting. Your weight actually fluctuates by several pounds in some instances. So, for example, this is on one of my treks to the Pacific Northwest on Mount Rainier. This is a 14,000-foot mountain in the Pacific Northwest, maybe a 2.5-hour drive from downtown Seattle, Washington State. So this is the highest mountain in the lower 48 states. One of my treks out there, did a lot of hiking and climbing. So I came up with a problem that was able to show that there is a difference, a small difference, but a measurable difference of my weight at home and my weight standing close to the summit of Mount Rainier. And it's a small difference, but it's non-negligible. So it's an interesting example to show the reader that your weight does fluctuate depending on where you happen to go. Now, from the gravitational force, we derive the gravitational potential energy. And so a small calculation shows what the gravitational potential energy is between two objects at a particular distance apart. So assuming your masses stay constant, changing your orientation between any two objects affects the gravitational potential energy that is trapped within that system. And we also calculate what the escape velocity is. If you're trying to launch a rocket, for example, into space, you need to get up to a minimum threshold speed called the escape velocity. For the Earth, this happens to be maybe about 7 miles per second, which is about 11 kilometers per second. This is the minimum speed if I were to go outside and take the spin, and I wanted to throw the spin into space and have it not fall back down, it would need to hit the escape velocity. So I would have to throw the spin at about 7 miles per second. If you're launching a rocket, much more massive than the pen, that's the very same escape velocity. So every object just leaving the Earth needs to overcome that minimum threshold of the same escape velocity, about 7 miles per second, about 11 kilometers per second. For each planet, it's different because each planet has a different mass. So it's a different gravitational pull trying to keep things from leaving the confines of that planet's surface. So the reader is shown how we can calculate what the escape velocity is. A bit of rocket science involved in here. Not just for throwing things into space, but launching satellites. You know, there are thousands of satellites, communication satellites, spy satellites, GPS satellites that are orbiting our planet at any given moment at different altitudes. So we actually calculate based on some geometry and trigonometry how fast and at what angle satellites need to be launched and what minimal speed it needs to maintain if it were to stay in orbit. Otherwise, the gravitational pull of the Earth would slowly cause the orbit to decay, and it would eventually burn up into the atmosphere. So to avoid that happening with a multi-billion-dollar satellite, it needs to be given a bit of a push every so often to keep it at this minimal speed as it orbits the Earth. And to do this, we study a bit of Kepler's work. Johannes Kepler was a child prodigy in mathematics sometime around the Renaissance, the great Johannes Kepler. And Johannes Kepler derived the laws of planetary motion, 3 laws in particular. The first law, you know, it's the shape of the orbit. You know, prior to his time, it was believed that heavenly bodies made perfectly circular orbits as they went around orbiting some other mass. We know today that's not true. Nothing makes a perfect circle of an orbit. It does not exist. Instead, elliptical orbits are described by the planets. An ellipse is like taking almost the shape of an egg. You take a perfect circle and you squish it down and it begins to bulge on the side. So that's Kepler's first law. Planets describe elliptical orbits, not circular ones. The other 2 laws are consequences, as we talk about in this chapter, in that as a planet orbits the sun, for example, at different days in that planet's year, it's at a different distance from the sun. So the gravitational influence changes. It increases and it decreases throughout the course of 1 year as that planet orbits the sun. And that, of course, changes the speed of the planet. Sometimes it slows down, it speeds up. It turns out that the further away a planet gets from the sun, and its maximum distance away is called aphelion, it's traveling its slowest. And as the planet gets closest to the sun at a location called perihelion, it's moving at its fastest. So even the speed of the Earth around the sun, as we go about our daily lives, it changes every single day. And the average person is really unaware of this, but it's quite fascinating, actually. And the very third law of Kepler, it says that the flatness of the orbit, what's called the eccentricity, the flatter the orbit, if you will, the longer 1 year would take on this planet, if you lived on this planet. So it's actually quite significant. It determines the orbital periods of not just the planets, but our moons, comets, asteroid, meteors, everything in the celestial heavens. And this is how we know we can predict Halley's Comet. It comes within eyeshot of the Earth every 76 years or so. It's a closed orbit comet. You know, we know this because of Kepler's work and others as well. And we can predict the behavior of threatening asteroids and other, celestial debris, like meteors and comets. Once they're discovered, we can look at their trajectories, how they're moving, their telemetries, and we can calculate how close they're going to get to the Earth, whether they're going to pose a threat or not. So much of this is based on the study of Kepler's work, Kepler's equations. So the flatter the orbit, the longer 1 year it takes on a planet. If you lived on that planet, it's quite significant. If you considered Mars, or maybe even consider the two extremes, Mercury's orbital period is about 88 Earth days. It's quite relatively short. But if you consider something like Neptune or even Pluto, if you still consider Pluto a major planet, Pluto takes about 248 Earth years to orbit the sun once. So we go from Mercury at 88 days to orbit the sun, and Mercury has an almost circular orbit. It's a very low ellipticity, compared to Pluto, which has a very high ellipticity. It's very stretched out, and that makes its orbital period very long, almost 248 years, as we said. So it's a significant difference. So several examples are worked on with Kepler's laws of planetary motion, because it's intrinsically related to gravitational attraction. And as with every chapter, multiple examples are done. Here's a picture of penguins in Antarctica. There are several penguins in here. And on my trip to Antarctica, as I watched these penguins from not very far away, as they jostled around seemingly without purpose, it was interesting to know what was the potential energy change between the system of the three of them, depending on how they're located. So it was a very interesting example. I sat there and I watched this happen as these penguins aimlessly walked back and forth with no rhyme or reason to it. It was actually quite entertaining. So I did an example of this about the changes in the potential energy of the system. And there are several worked examples. Also, there's a fascinating example on tides. I mentioned that the moon, it tugs on the ocean waters, creating high tide and low tide in different places on the Earth. And nowhere is that better seen than off the coast of Newfoundland in the Maritimes of Canada, in a place called the Bay of Fundy. So I'm overlooking the Bay. I had to go see this myself. I could not believe it when I first learned about it. So I traveled to the Maritimes of Canada, and so I'm at the Bay of Fundy, and I'm overlooking the rise and fall. And this is the height of the rise of the ocean level, if you can see where the grass starts and where the water level happens to be. So where I'm standing here, all of this, it's difficult for the reader to see, but I'm standing right here, and the water level gets to about here twice a day. You can almost see the ocean rise by 3 feet every hour, and also drop 3 feet every hour. The Bay of Fundy is the highest tide on Earth, a 50-foot rise, a 50-foot rise in ocean levels twice a day. Highest tide on Earth at the Bay of Fundy. The volume of ocean water necessary for that to happen would take every river on Earth all flowing into the same spot at the same time to be the equivalent of how much ocean water needs to flow into the Bay of Fundy to cause a 50-foot rise in ocean levels. And it happens twice a day. And like I said, there are multiple worked examples just on the Bay of Fundy and the change in potential energies of the system. So I think the reader will have a fantastic idea of how gravitational influence affects our planet. Thank you for listening. Bye-bye.